This is group M9. We're going to be talking about the corrosion protection on suspension springs of race cars. So for our project, we've chosen to research about the corrosion protection on automotive suspension springs and its prevention using some type of powder coating or wraps or phosphorus coating, and to protect the springs in this harsh Canadian environment. The springs are particularly susceptible to corrosion in winter due to wet conditions, and the salt that we use on our roads, it can go through anything usually. And with the powder coating on the spring, without the powder coating on the spring, it would spontaneously corrode in this environment and quickly sacrifice the integrity of the spring and will ultimately lead to failure. What is different about these springs compared to our normal car springs is these need to be stiffer and stronger due to the track and how fast these race cars are going compared to how these commercial cars are going. These cars usually on track will go 200 to 250 kilometers an hour, and due to bank curves, these strings need to be stiff and keep the car grounded. So if they're approaching a turn at, say, around 200 or 150 to 200 kilometers an hour, the spring needs to be able to support that weight when turning, and the centrifugal force would not tip the car off or let it spin out in any type of way. Now looking at the design requirements and the material requirements, it would seem like aluminum would be a pretty good fit as a material for the spring because it's light, it's pretty elastic, it's semi-strong, but we're also postulating that steel might be a really good material for this as well due to how stiff it needs to be, but also how strong it needs to be to support the weight of the car and support the speed at which it's moving. Considering corrosion protection, it would seem like some type of coating or some type of wrap would be pretty good on this. Some cars, like the one here, has a matte gray wrap on it, which would help with corrosion protection and rust protection on the aluminum body. The base cars, when they get older and are really the cars would be susceptible to a lot of salt and dirt and a lot of moist winter conditions, which Canada has, which lead to the bottom of the car being really rusted and corroded over time. And this wrap really helps protect that initial aluminum coating and gives it the extra barrier for corrosion and rust to go through.
The functional requirements and design specifications of our spring are to, firstly, withstand the centripetal force of the car when turning. This is the force that the car undergoes when it hits a turn at a relatively high speed. Furthermore, the spring must keep the vehicle in level to ensure traction and ensure aerodynamic efficiency. The car must be above the ground so that it's not hitting it and injuring the chassis, but be low enough so that air can smoothly ride over the vehicle. Moreover, the spring must expand and compress back to the original length to keep balance of the vehicle, and if it does not go back to its original length in quite some time, it compromises the ability of the vehicle to ensure that balance. And finally, the spring must absorb shock from the roads effectively to avoid damage to this chassis, and rebound in time to ensure a balance.
After calculating the shear stresses, the forces applied, and how much cycles per life we would need by this certain spring, we're coming to the conclusion that a AISI 9255 steel alloy would be really beneficial for this application. This alloy contains carbon, silicon, manganese, sulfur, and phosphorus, and they're useful for a lot of the material properties that make up this alloy. Starting with the shear stress along the coil, near the coil, this shear stress was calculated assuming that the road was smooth and the car was going at 200 kilometers an hour, and this was calculated to be 510.5 megapascals. Now we assumed a factor of safety of 2 by simulating a certain size of bump and then calculating the max shear stress that would be applied. From there, we're calculating or assuming firstly the general functions of the spring itself. You would say that it's loaded uniaxially. It's the most load that it can support is F. The most it should not be able to compress more than a certain amount on full load. If it compresses more than that, it would fracture right away. And this unloaded length is fixed, and so is the inner diameter. Now, if it were to compress more than, like on, for example, on a turn, if it were to compress more than it should at a full load, the spring would collapse and the car would bounce off or spin off or not be able to return back to its handling position. Now, since these are alloying steels and the design requirements that we need are not more of cost but more of strength, we chose to do this in 5 stages. Stage 1 would be yield strength versus density. Stage 2 would be shear modulus versus density. Stage 3 would be corrosion resistance in salt water. Stage 4 would be price per unit volume versus density, and stage 5 would be metal cold formability. These springs are initially made from cold forming, and then they go through different treatment processes to form them into the mechanical and material properties that we desire. Now, if you see on the right, those are the scores for all the materials that we have tested. ANA ISI 9225, quenched, fine grained, and tempered at 205 degrees Celsius has the lowest score, and in our case, the lowest score means the best material. So what we did for cost versus strength was we multiplied the performance factor by 2 compared to the cost. This is because in race cars you need a better performance than cost. We're not going to make 50 of these race cars. We need one race car, and we need to put a lot of effort and money and good design into it so that it performs really well. But in commercial cars, this is different. In commercial cars, you need to mass produce hundreds and thousands of cars, and the cost is a really important factor in that. Strength is important. However, max a car is going to go on a highway is 100, maybe 150, 160. It does not, and it's a straight road. It does not reach the limits of a race car turning, on a bank curve or any of those types of road conditions. Now, corrosion resistance in salt water is also really important, since the graph from the CS EduPack proved that the material is in the limited use to accepted range, and this would mean that the material would not corrode, well, not spontaneously, but it would corrode over time as all materials, but this would not corrode spontaneously. It would help in the rigidity of the car, the handling, and overall the compressibility, the rebound, and all those types of mechanical properties listed. When considering heat treatment, it is important to consider quenching, tempering, and sometimes fine graining. But in steels, like ferrous metals, steels have a lot of phases that it can go through depending on how you quench it, how you temper it. It goes for how you etch it and stuff like that. And in this case, this one was quenched and fine grained and tempered at 205 degrees Celsius, meaning that this would mean that for this specific material, we would need to quench, fine grain, and temper it at 205 degrees Celsius to produce the specific shear modulus, the yield strength, and all that needed for this application. Now, depending on what temperature it is quenched, it could have a different, or even tempered, it could have very different material properties. And comparing to other different types of steels listed here, it produces the highest yield strength and also the highest Young's modulus, which is very important in this application.
Suspension springs in the car are protected from rust, corrosion, and scratches by a type of powder coating. This is the finishing process that the springs ultimately go through. So in order to apply this coating, the base material must first be prepared by cleaning it. Then the metal is dipped into an acid, and this process is called phosphate coating. There are three main types of this: manganese phosphate coating, zinc phosphate coating, and heat-stable zinc phosphate coating. The phosphate coatings are applied by dipping the metal into the solution of phosphoric acid and phosphate salts, or having the solution directly sprayed onto the material. The chemical reaction between the solution and the metal form a layer of insoluble crystalline phosphates. This process gives a base protection to corrosion and helps with adhering the powder coating to the metal. The powder coat is typically applied by a process where high voltage is applied to the particles as they are sprayed, so that they stay on the metal until it is heated and the powder melts, forming a layer on the metal to further protect from corrosion and rust. Both of these coatings isolate the spring from the outside environment, leaving the metal inaccessible to road salt and water. The image on the left shows the charged particles of the powder coat as it is applied to the phosphate-coated motorcycle chassis. This would technically be the same way though that the powder coat is applied to the springs. The image on the right are 5 completed powder-coated springs that are ready to be installed.